Welcome to this module, and in this module we will be looking at another way of understanding the tissue property, that is using the electrical modality. Until now what we are looking at the tissue properties where one, a biochip that can help us to understand the electrical, mechanical and thermal property. Then we have seen a piezoresistive microcantilever that can help us to understand the elasticity of the tissue. Now let us see another sensor that we can develop to understand the resistance or impedance of the tissue, right. And then we will also see a flexible sensor which can understand the electrical and mechanical property of tissue. So, this will be the complete lecture for us to understand. So, let us see the slide. In the slide what we have seen is what we can see is a piezoresistive microcantilever, one with silicon nitride and one without silicon nitride. This is without and this is with silicon nitride. Okay. So, if I use this piezoresistive cantilever to indent the tissue, what will I find? I will find the elasticity of the tissue, and you see the elasticity parameter right over here. I do not worry about the resistance now, we will see how can we measure resistance at some later stage of this module. But you can see here that if I consider 8 different patients and epithelial region in a normal, so a single patient we have done for 8 different patients. I am showing it only for a single patient, tissue or a tissue from a single patient using biopsy. So, it is a biopsy tissue on which we are indenting the piezoresistive microcantilever in this way, and we are indenting at 8 different places within a given ROI, within the given region of interest. We are indenting tissues at 8 different places, and we, so that if this is the tissue, for example, this is a tissue and this is a region of interest, then we will indent in this region at 8 different places to get the tissue property out. So, when we do that, we can see that for epithelial region in a normal patient, right, a tissue taken from a normal patient, the elasticity is less, but when we take a tissue from a stromal region, it is more. Compared to stromal and epithelial, for a normal elasticity is less compared to stromal. But if I compare invasive ductal carcinoma, this is invasive ductal carcinoma. So, this is a cancer tissue from the cancer region, and what we see here is that the elasticity in epithelial region compared to the epithelial region of a normal patient is extremely less, is actually around 15 kilopascal or 10 kilopascal, where you can see that elasticity values for epithelial region in case of normal is around 40 kilopascal. Even if we talk about the stromal region, you can see that the stromal region here is about 20 kilopascal, where here is around 80 kilopascal. Thus, what we see that there is a change in the elasticity of the tissue or the stiffness of the tissue in case of cancer patient compared to normal patient, and thus using a piezoresistive cantilever we can understand whether a tissue is from a normal patient or is from the cancerous patient based on the elasticity value, right. Thus, our exercise of understanding or fabricating or understanding the process flow for designing the piezoresistive microcantilever helps us to measure the tissue property, in particular elasticity or you can say stiffness, right. So, that was the idea of making you understand the importance of piezoresistive microcantilever. Now, let us quickly see what we have seen. We have seen a biochip that can help us to understand electrical properties, mechanical properties and thermal properties of a tissue, right. Electrical properties, mechanical properties and thermal properties of tissue. Then we have seen a piezoresistive microcantilever that can help us to understand the mechanical property of tissue, right. So, mechanical properties are elasticity, or you can say stiffness, right, elasticity or stiffness. Now, let us see a different sensor that can help us to understand the electrical property of tissue. All right. So, if you see the slide, here you see is a 4 inch oxidized silicon wafer on which there are several sensors around 30 sensors, and each sensor has an interdigitated electrode. Each sensor has interdigitated electrodes, okay, and over the interdigitated electrodes we have a SU8 boundary. So, what does it mean? Let me show it to you. What does I mean? I mean that there is a SU8 well, and in that SU8 well, so actually this is a oxidized silicon wafer. Let me draw it a little bit bigger diagram. So, you guys get it. The cross section, oxidized silicon wafer. So, we will have oxide, here, right. On the oxide, what we have? We have interdigitated electrodes, and over that we have SU8. So, what is this? This will become like a well. This is SU8, this is silicon dioxide, silicon, right. This is SU8 well. This is what is shown here, that microsensors with interdigitated electrodes inside a SU8 well. The schematic or a schematic representation of this device is shown here, where there is a passivation layer, because it is a silicon, that is why we are using silicon dioxide as a passivation layer. There are interdigitated electrodes, which you can see the actual photograph right over here, and then our chip consists of those interdigitated electrodes. Now, what we will be doing? We will be measuring the impedance or the resistance of the tissue. We are measuring the resistance or electrical property of the tissue when you place the tissue on the interdigitated electrodes. Now, if you see here, each electrode has 10 micron spacing and the width is also 10 micron. Width and spacing is 10 micron. What I mean by width and spacing is, like you see this kind of lines, right, like interdigitated. So, like these lines are there. Right, these kind of lines are there here, 1, 2, 3, right. So, the width is 10 microns and the spacing is also 10 micron. Width and spacing is 10 micron in this particular case, right. That is what we mean by interdigitated electrodes with 10 microns spacing. So, now let us see, if I place a tissue on this interdigitated electrode, this is what is shown here in this schematic, that we are placing a breast tissue on interdigitated electrode. What will happen when you place the breast tissue on the interdigitated electrode? There will be change in the impedance or resistance of the device, right, because right now interdigitated electrodes are not touching each other and these are metal lines. So, your resistance should be infinite because they are not touching, right. When you place a tissue on this, because of the resistance of the tissue, what you will find? You will find that the tissue from cancerous region would have a different resistance, a tissue from cancerous region would have a different resistance compared to the tissue from normal regions. So, a normal tissue or a benign tissue will have a different resistance compared to a tissue taken from ductal carcinoma in situ or invasive ductal carcinoma. So, now it is a easy way of understanding the electrical property of tissue just by placing tissue on the glass slide containing a SU8 well, and inside the SU8 well there is an interdigitated electrodes, such that the electrodes are on the oxidized silicon wafer and on the side there is SU8 well. Now, what is the point of making SU8 well? The point of making SU8 well is when you load the tissue, you have to keep the tissue in a saline solution so that it does not deteriorate. So, when you load PBS, if you do not have the SU8 well, the PBS will be spilled out from the tissue region. So, if you see here the load, if I place the tissue right over here, right over here, if I load the solution will be contained, this is like let us say PBS for saline, the solution will be contained in the SU8 well. If I do not have the SU8 well, my solution will be out, right. So, let us now see how can we fabricate the interdigitated electrodes on oxidized silicon wafer, alright. So, let us quickly see, it is very easy, just a 2 mask process, it is a 2 mask process. Now, you should know, because we are fabricating SUA interdigitated electrodes in SU8 well, inside SU8 well. So, what we will do? We will take a oxidized silicon, we take a silicon wafer, right, silicon, then we will clean the silicon wafer, then we will grow oxide on both the sides, oxide, okay. Now, after this next step is we will spin coat, is correct, we will spin coat the photoresist, is correct or not. What we want? We want interdigitated electrodes inside SU8 well, right, inside SU8 well. This is what we want, okay. So, this is our SU8, this is SiO2, this is silicon, this is SiO2, alright, this is what we want. So, now we have oxidized silicon wafer, this interdigitated electrodes, these are interdigitated electrodes. These IDEs are made out of what? IDEs are made out of metal. So, we can say chrome gold, chrome gold. So, on the silicon dioxide, what we will deposit? We will deposit a metal. We will deposit a metal. How? By using PVD, physical vapor deposition, either E-beam or thermal. On this we will do lithography. So, we will spin coat positive photoresist, right. We will spin coat positive photoresist, then we will do soft bake at 90 degree centigrade 1 minute on hot plate. After that we will load our mask will have the pattern that we want for interdigitated electrode. Now, this is a bright field mask, field is bright, pattern is dark, bright field mask, and bright field mask, right. Over this, what we will do? We will expose. After this, we will expose the wafer or photoresist with UV. After exposure, next step would be PR developer, right. PR developer. When we develop in photoresist developer, what we will see? We will see metal and then photoresist only in the area which was not exposed in UV light, because it is a positive photoresist, right. So, unexposed area will get stronger. After this step, next step is hard bake 120 1 minute hot plate. Next step, after this the next step would be etch in chrome gold. So, what you will have? You will have oxidized silicon wafer, with interdigital electrodes, but there is what? There is a photoresist. So, next step would be to dip this wafer in acetone. Acetone will strip off the photoresist, right. Acetone will strip off the photoresist. So, here if you see, the photoresist is protecting the metal which is below it, and the metal which is exposed will get etched in chrome gold etchant, followed by which we have to strip off the photoresist. So, we are dipping the wafer in acetone. When we dip the wafer in acetone, what you will have is interdigitated electrodes. What you will have is interdigitated electrodes. So, this is our mask 1, right. But what we want? We want interdigital electrode to be in SU812. So, let us see how can we do that? Interdigitated electrodes in SU812. So, in the last slide what we had is oxidized silicon wafer, and on oxidized silicon wafer we had interdigitated electrodes, right. We had interdigitated electrodes. Now, this is chrome gold, this is silicon dioxide, this is silicon, and this is silicon dioxide. Now, what we want? We want SU8. So, we will spin coat, SU8, which is a polymer and it is a negative photoresist. It behaves as a negative photoresist. So, we will spin coat SU8. After spin coating SU8, you know what you have to do? You do soft bake. Soft bake is done at 65 degree centigrade for how much minute? Depends on the thickness of the SU8. After that, What is the next step? Next step is I will load the mask, right. I will load the mask. What I want? I want to protect SU8 in certain region and H SU8 from the unwanted region, right. Right. So, here the unexposed region would be weaker, unexposed region would be weaker, right. So, I want to have a mask such that my unexposed regions becomes weaker. So, I will have a mask like this and is this correct? No, right? What do you do? We have to open the region over the interdigital electrodes and over the contact area, right, over the contact area, right. So, now this is my mask 2, this is SU8, these are interdigital electrodes, this one is silicon dioxide, I have silicon wafer, what is the bottom layer? Silicon dioxide. On that what we will do? We will expose the wafer, we will expose the wafer with UV, right, with UV. After that, next step after exposure for SU8 would be to hard bake, not to develop. Okay. First to hard bake. Hard bake is done at 95 degrees centigrade. Again the time depends on the thickness of SU8. Time depends on thickness of SU8. Okay. After hard bake, I will go for SU8 developer. I will go for SU8 developer. If I go for SU8 developer, what will I have? I will have oxidized silicon substrate with interdigital electrodes and SU8 well, right. I will have oxidized silicon wafer with interdigitated electrodes inside SU8 well. Easy, that becomes your chip, and on this chip what we will do? We will place the tissue, and we will also use a solution to keep the tissue intact. That solution is our PBS. All right. Now, if I want to measure the resistance, I can measure between these two contact. I can measure the electrical property. Now, if you understand in detail what is the difference between resistance and impedance, you will say that we should measure impedance because there is a parasitic capacitance, also there is a double layer capacitance and other parameter that comes into effect. So, we cannot rely on resistance, we should rely on the impedance measurement. And thus, we will see that when you place different tissues on the interdigitated electrodes or over the interdigitated electrodes, you will see that the impedance of the tissue changes as cancer progresses. Thus, you can use electrical property, which is an impedance, as a parameter or as a modality to understand the change in the tissue property when the tissue is cancerous, or if the tissue is from normal region, or the tissue from intermediate region, right. So, the change in the tissue property, that is electrical modality, can act as a parameter to understand what is the stage or what is the type of the tissue that we are measuring, right. So, now what we have seen? We have seen a mechanical way with this elasticity, we have seen a electrical way which is impedance, we have also seen electrical, mechanical and thermal way which is a biochip. So, in the next module what I will teach you is a flexible sensor that is integrated with a piezoresistive sensor and a gold electrode, but now everything is on flexible material which is your PDMS. So, till then you concentrate on this particular module. If you have any questions, feel free to ask us through the forum, right. And this is just one example where I am asking you to use the sensor and place the tissue on the sensor to measure the change in impedance, but you can also use this for understanding the change in the cell property, stiffness of the cell, right. If you can measure stiffness of tissue, why cannot measure the stiffness of cell with the cantilever? You can. Why, if you are measuring the resistance of the tissue, why cannot measure resistance of a cell? You can, right. Are you or are we limited with only breast cancer? No, we can use any tissue related cancer, oral cancer, prostate cancer, right. You can use any tissue related cancer to understand the change in the electrical property, right. Till then you just look at the module and I will see you in the next class.